This is being recorded as usual and will be available. And don't forget the mic. You can unmute yourself if you want to ask questions in the middle. Don't be shy. I'm open to any questions at any time. What we will be doing today, and probably also in the next lesson, and possibly even the third lesson, is what we'll be learning everything we need to know about iMachining. As you know, iMachining is one of our flagship modules that we have today inside the SolidCAM, and especially when talking about the tool performance, this is extremely important to know about this. So what we're going to do today is first I'm going to start off with a little presentation explaining about iMachining, why iMachining, and so on and so forth. And then afterwards, we'll start actually working in the program, showing how it actually works. And again, at any point, if you feel you need to ask questions, go ahead and just unmute yourself and ask the question. Okay. Now, just a little introduction about iMachining itself. What exactly is iMachining? iMachining is a new technology. That's so new anymore. We had it for quite a while, but it's a technology that allows you to increase dramatically your tool life. Also makes your cycle time about 70% or even more shorter in many cases. It's phenomenal when it comes to working with hard materials. The harder the material, it works even better. And also, we're working with small tools. Working in hard materials, even small tools are made very easy. It can easily be done when using iMachining. I know I've noticed also for a very good fact. I've used in certain cases, a 2 millimeter end mill, and cutting at a depth of 4 millimeters without any problem, just whizzing through a piece of 4140 without any problems. So when you see something like this performing on the machine, it completely wows you. We also have this working inside our 4-axis indexial as well as inside mill turning in iMachining as well. The programming at productivity, it's very quick, very easy to program it. So also the learning curve, very easy to learn how do you work with iMachining. Now, basically, iMachining has what we call the iMachining toolpath and the iMachining wizard. Now, what exactly is the iMachining toolpath? It's an intelligent toolpath generator. It calculates the efficient and most tangible toolpath, which ensures constant mechanical tool load. In other words, what we're doing is we're always trying to do a constant tangential toolpath. All the toolpath is always tangent. There's no such thing as a sharp turn inside iMachining. So the toolpath is always constant. There's always a constant load on the toolpath. And the other thing we're talking about inside iMachining is the technology wizard, which actually does the calculation of that of the toolpath itself based on certain facts that are given by the operation itself. And we'll talk about that as we go along. Now, what are the problems that we normally face when working in the traditional manner, I like to call it? Well, if we take this, for instance, this pocket over here, now the pocket geometry itself may be a tangent on the corners, and the entire toolpath is tangent. But when doing the racetrack path inside a normal pocket operation, when you get to the corners, you'll always have sharp turns. That in itself causes vibration, which is no good. Okay? So you have what they call non-tangent toolpaths. Also, you're causing, in many cases, especially with cases like this, overload on the tool, where the tool itself goes more than goes even up to 180 degrees of the radius of the diameter of the tool, and that is actually not good for the tool itself, causing negative effects on the tool. Also, cleaning these corners, which you have to clean around the part, you always have excess material on the corners. So normally with this type of tool path, the race path tool path, in order to clean that area, you're going to have a tool path that goes around in the air. So you're wasting all that time. Okay? Also, with traditional fixed tool path, you have a fixed step over, which is not good also, especially in tight corners. Okay? So what happens? The CNC control, the operator himself, he has to slow down. He has to work slower. And he also has to take shallow cuts to avoid, to deal with these type of situations. Now, even though you may need a slower cut for a specific area only, but since you have to do it in those areas, the entire tool pass is a lot slower. And you're also cutting with a small amount of the tool because you're taking shallow cuts. So, excuse me. So the cutter life is, since you're only cutting with a small part of it, you're not getting the full use of your tool. You're going to wear out the bottom of your tool a lot quicker also. And you're also working a lot slower than you really can work. Now, what do we do in iMachining? First of all, we have the intelligent toolpath, where in any kind of, you'll see that we have a smooth tangent toolpath. The toolpaths are always tangent. As you see, we have here a spiral, and even when you get to the corners, we have trochoidal cuts where there is no such thing as a sharp turn. You can see that very carefully, very clear over here also in these particular cases where the step overs are completely controlled. And we'll talk about that further on. Also, we're cutting the exact stock. There is no such thing as air cutting. It'll only cut where it needs to cut. These areas, it will not work in those areas. And just jump over to the next area. So as I said, we can take deeper cuts because of that. Okay? You're cutting with the entire tool. And we're also controlling our engagement angle over here. We'll never over-engage the tool itself inside iMachining. Now, another important thing is the feed rate when creating the tool path. Well, we have what we call here a morphed situation, where the tool path actually gets the controlled step over. Sometimes it's wider, sometimes it's shallower. So we actually control the feed rate at any single point. So what that means is that no matter where you're cutting, your load on the tool, your chip thickness on the tool is constant. When you have a constant tool chip, the constant tool load on the tool, that also greatly increases the tool life. Also, not only that, we have what they call repositioning. In the cases where it doesn't cut in a spiral cut or a morph spiral, where it does a trochoidal cut, the repositioning is done very smartly. It keeps itself down and it goes there very quickly, knowing exactly where it can move quickly in a rapid and and repositions itself in those areas. So when you do that kind of a repositioning in these areas over here, you don't need to go around the part. So that takes care of unnecessary moves and also eliminates the air cutting. Now, as we're cutting itself, as I said, we also have complete control. We control exactly the minimum and maximum cutting angle of what our tool will be cutting at the time. Also, depending on the material, we can go from anywhere as little as 10% up to 80% of the tool of the tool angle over here, cutting angle. And you can see that when we're working on, let's say, 20 degrees, you'll get a smaller feed rate. Whereas working at a higher angle, so even up to 80 degrees, you get a slower feed rate. You get a slower one here and a faster one over here. Here, there's less of a load, a less of amount of material, so we can go faster to keep the load constant. Now, another important feature that we have inside iMachining, I've mentioned some words about this before, is we all know that a spiral cut is the most efficient way of cutting. Okay, but not everything is a perfect spiral, as you can see in this part over here. So what we do is we have what we call a morphed spiral, where it actually takes into consideration the shape of the area and starts morphing itself slowly but surely into a more of a spiral shape in the beginning. You can see in the middle, it's more of a spiral, as at the end, it actually morphs out towards the actual shape. And this is what I mentioned also before, that here you'll have smaller side steps, whereas over here, you'll have larger side steps. Now, there are certain cases, what we'll do in cases like this, where we can't go around, we can't be a spiral cut. For instance, we have a wall on one side. There's no way you can do a spiral. And what we'll do is we'll do a channeling. We'll make what they call a moat or channel around these areas over here, creating different areas. And after that, we will spiral out those areas, because now we can machine around from this side and this side and this side, now that this material has been removed. We also have complete control of the efficiency of the spiral. Okay, we actually leave that to the user. We have a specific setting that we have inside the program, which we tell people you don't really have to touch it. But if you want, you can also decide on how much of a spiral you want. Sometimes you can say, you know what, I want to have a very tight spiral. You see, so the side steps here are pretty much equal. But then to clean out those areas together, you need trochordal cuts. Where if you have more of a morph spiral, you can cut more of an area with the spiral cut. As I said, a continuous spiral causes less wear on the tool. Okay. Now, let me go a little further. Now, why do we need the moats? I think I just explained it. So it allows the tool path to go around and create the spiral cuts that I mentioned before. Now, we can see that actually very clear in this picture over here. If I were to do a complete spiral cut, just a minute, okay. If I can do a complete spiral cut, a morph spiral on this entire part, which I can if I want to, you'll see that these side steps over here are very, very small as compared to this. Now I can do that without any problem. Of course, may have a little less wear on the time, but the amount of time it takes to cut this is a little longer. You can see when we cut something like that, like this, is 5 minutes and 4 seconds. Okay. However, if I put in here the channels over here, the separating channels, as you see over here, it'll separate those areas and then continue with a spiral cut in each area itself. So what that does, it also cuts down on the machining time. Now, in iMachining itself, the algorithm that is used actually measures everything and decides on its own which is the better way to cut. But again, we also give you control if you want to do it differently. This can also be seen in cases like this. You can see over here, we have a wall and a large area over here. Now, if I wouldn't put a separating channel, this is how it would cut. It do constant trochoidal cuts around the part. Okay? Sometimes you have no choice, and we'll explain that a little later on why I wouldn't have a choice to do that. And there are other times where it's better to do a separating channel and then do your trochoidal cuts and your morph spiral over here. Now, let's say I have an island over here in the part. How do I keep it from, and I was working from the outside, how do I keep it to do a spiral cut as much as often as I can? What we do is when we get to this point over here, to a certain point, we can do a spiral as much as we can, and then we do a moat around the island, okay? Or a separating channel. We form a separating channel around the island, allowing us to do then more of a morphing inside, of a morph spiral inside the part itself. Now let's just take a look at this particular part here. We have to machine out this pocket, okay? So in the beginning, it's starting with a morph spiral, okay? But now it's hitting these islands. So what it does is it does the separation by those little moats that I talked about around the actual island itself. Once it does that, it can continue now with more of a morph spiral up until it hits these walls over here. Then it continues with a separating iron around here. Now it did a little more of a spiral and also trochoidal inside over here as well. And that's how it works. Now we also have a function called rest material. For example, if I was able to machine a part, but obviously I'm not going to machine a large part with a small tool if I have small radiuses. So for the rest material, we'll only machine in those areas that have to be cut, such as these corners, and using a trochoidal cut in this particular case. And even in the areas where it couldn't get into over here, it'll also complete finishing those areas. And when I do a finish cut, if I had those, it'll first do a semi-finish in the corners, doing trochoidal cuts, and its final cut will go around the entire wall, giving it for a nice smooth finish. Now you can also see that when we cut out parts with closed pocket, we also do a helical ramping into the pocket to get down to the bottom, and then finish off whichever tool path we need to use. We can see that very clearly over here. Now let's take a quick look at this film. I hope you can see it as well. And I want to get to a specific point. I want to get to this point over here. We've machined the outside. Now we have to start machining inside over here. Now what you see actually happening is the tool actually going inside using a helical ramping, the 10 millimeter end mill, and it's going down to a depth of 19 millimeters. Now look what happens when it hits the bottom. What happens with the feed? You can see all of a sudden the feed picking up. Now we're just doing it in slow motion, so you can see exactly what's happening. You can see it doing a morph spiral cut around the part, which is constant load on the tool, giving you the most efficient way and the best way to cut with the tool itself. Now, when a typical programmer has to cut out material in the part, what are the dilemmas he always has to do when programming in the traditional way? One he has to take in consideration, even the most experienced machinist has to take into consideration, one, the type of material that he's using, what kind of cutting speed he needs for that material, the hardness of that the material takes into account, what's his maximum step, what's his minimum step into the part. This is something that the user always had to do on his own. As far as the tool goes, he had to know the excuse me, the what type of, the length of the tool, the number of flutes, the helix angle he had to take into account of the tool, chip thickness that he's allowed with the tool itself. All of these he had to know just by experience. Now, with the geometry, he always had to take into consideration how deep he has to go with each cut. And in the machine itself, he had to know himself what's the maximum spin rate or feed rate, the power of that machine, the memory size even of that machine. He had to take that into account. Now, iMachining deals with all that. Okay, together with the technology wizard, it takes into consideration your material, your geometry, the tool that you're using, even the machine, and takes all of that, puts it together, and gives you the right G code for what's exact the way it should be done on the machine. Now, it should be noted also that iMachining is patented by SolidCAM itself. Now, there's one other thing that we have inside iMachining, something called the iMachining level slider. And we'll talk about it, and I'll show you this to you also later on as I show you the actual program itself. Now, what's the role of the iMachining slider? The iMachining slider allows you to be more aggressive on the part, and working even also in a less aggressive, a little more safe mode, I should simply might call it. Okay, it actually controls the removal rate.
Sidney?
Yes, go ahead.
I have a question. When you say more aggressive or less aggressive, and I know this line over here that you're using over there.
Okay.
But it's control the speed, I mean the RPM and the feed equal. Yeah. Okay. So now if I want to separate it and just control all the speed or the feed separately, can I do it here?
You can do that in the modified cutting conditions. Okay, but take into consideration. But you said something that over here that we control this. The levels control the speeds and feed rates. That's not all it controls. Yeah. It also controls your minimum and maximum step over.
This is another thing load.
And also, when you're, and I'll talk about this again, is that even though you may see a specific feed rate over here, that's not, that's maybe your average feed rate, because your feed rate will constantly be changing depending on your step over at that point, your chip thickness at that point. Because we try to control the chip thickness with by stepping over with the morph step over as it changes. To keep the constant load, you have to constantly change your feed rate. And that's what we do.
Yeah, but it depends the pocket. For example, if it's an inside pocket and you have a line, straight line, it's not a problem. But when you get closer to the radius, then, if I understand right, the thickness of the chip is a bit smaller.
Actually, that depends on your feed. If all of a sudden you slow down on your corner when you get to it, okay, your chip thickness will be the exact same as it was before. Because remember, we're not doing any sharp turns inside there. Even when you get to the corner, it will not make a sharp, it will not do to a point and all of a sudden sharply turn. It does a trapezoidal turn inside the corner. In other words, your tool, it will never have a radius of the exact tool radius. Okay?
Yeah.
Now, the technology works, it makes its decision knowing the following. It knows the part geometry, the material properties, the tool properties, and the machine limitations. Okay? Now, the algorithm works hand in hand to give you the exact tool path generator with the proper feed and spin rate and the proper step over, making it very safe to work on the CNC at the very first time. So you may ask, why do I need a level slider? I mean, why not work all the times with the highest level if we're controlling everything? The answer is very simple: potential vibrations. And what do I mean by potential vibrations? Okay, there are certain things we know. We know the tool, we know the material, and we know the geometry, and we know the capabilities of the feed rate and the spin rate and the horsepower of the machine. All that we know. There are things we don't know. One, let me go to the next thing. There are certain things we don't know. Okay, let me go into that. Sorry, I went back a little too quickly. Okay, we don't know the rigidity of the state of the machine. In other words, if it's an old machine that has more backlash, how you maintain your machines, those are things the program doesn't know. That's only the user knows. Okay. Also, when you're clamping the part, the workpiece, onto the table, we don't know how well you're holding apart. If it's a really rigid uh, um, fixture or some lightly used clamps, okay? These are reasons that you need the iMachining level slider to allow you to decide what level you should be working on, okay? For instance, the metal removal rate is associated with the minimum metal removing rate is associated with level 1. Okay, so there it's being extremely safe. Okay, and I'll show you examples in a moment where for example, you'd use a higher level and where we'd use a lower level. Okay, the maximum, of course, is level 8. 2 and 7 is what they call the intermediate. Okay, now there are times even with certain materials where 8 is not enough. Even going up as high as 8 is not enough. So in our modified cutting conditions, we have something called turbo mode, which actually takes the levels and ups it by 25%. So you can get, for instance, like in aluminum, we found that you can even go higher. And many times I've even demonstrated aluminum working. I remember the first time I had demonstrated this for a person, I went to his tool shop, and he had a 90 millimeter deep pocket, and he was using a 16 millimeter end mill. And I was using, and he had like a 30 millimeter depth of cut, I believe, on the end of at the end mill itself. I put it on the machine. He had already pre-drilled a hole, even though he didn't have to, but he's already pre-drilled a hole. And I put it on turbo level 7. And he said, "Are you sure?" And I said, "Don't worry about it. Tool breaks, I'll replace it." Okay? He started working, and all of a sudden, you hear the noise coming around. He's jumped away, and all of a sudden he starts looking. The person the owner of the shop came down to the machine. He said, what's going on here? And he saw how much material was coming out, and he couldn't believe what he was seeing. At the end of the cut, we looked at the tool. The tool looked like it did not even work. In other words, it was like a brand new tool. And he said, "Do it again." And I did it again. And 3 days later, he called up and he bought 2 more stations, both of them having iMachining on them. So just to show how efficient these things actually work, that's what iMachining was. But let's go further now into the program. Okay. Now, when defining a machine in iMachining, we can define also what's the default machining level. In other words, you have a specific machine, you know already how this machine works, you can set yourself what you want as a default level. It doesn't mean you can't change it inside the program itself. Now, another important point that we take into account is that when we're cutting is the actual cutting points. Okay? We call it ACPs. Like this ACP equals 1. Okay? Notice when cutting over here, we're getting over there, we have what we call 4.5. Okay? The closer to an exact number you are, the less chance you'll get vibration. Okay. Now, as I mentioned before, it reflects the actual number of contact points during the vertical walls in cutting along the lines. Okay. Example. Now, what I mentioned before: 1, 1.1, 1.2, 1.8, 1.9. You notice these are close to full numbers, to whole numbers. The vibration over there is less likely. Okay. Whereas you have something like 1.4, 5, 6, or 2.4, 2.5, 2.6, you have more of a chance of vibrations. So we can control also the down steps if we want. And some people also we can they're willing to work even in those conditions. But just know that we take that into account when working with iMachining. So for example, and we also mark it, by the way, inside the technology wizard. You'll see sometimes the amount of steps. You'll also see the step down, and you'll also see the total step down, how many steps down it has to do each time, and you'll also see that it's in red. Okay. Sometimes now if I mess up with the colors, excuse me, I'm colorblind, but it happens every now and then. But okay, yellow, it's not so good, but it's pretty good. Here, this one over here, see, you have 1.9. It's very close to a high number. That's an excellent cutting condition. Okay. So I've talked. So the level also the level slider also helps control with the vibrations because you're putting inside. You're putting in the right amount of pressure exact that you need for each particular case. That now, once you have everything set, you're ready to cut. Now, and I always recommend when working on iMachining, when you first start out, you're not sure, always start out with a lower number. Okay? You listen, you hear there's no vibrations, you can start working your way up until you get used to it the very first time. Once you start working with iMachining on a constant basis, you'll know already by yourself. But in the beginning, you don't know about it, start always with a lower level. Now, I mentioned before of what kind of situations you would do different types of machining levels. So for example, if I'm holding part clamped in a machining vise, pretty rigid way of holding, I'm not talking about the machine condition at the time. I'm talking about right now the clamping situation. This particular clamping situation, we could go even as high as 8. Okay? A 5-axis clamping position held very well can also go many times up to 8. Holding it clamped on a picture plate is not always as well as sometimes you have no choice. Okay, so in those particular cases, you may start off with the 4. Okay, even with a clamping plate like this, hold on 4 screws. You may also want to start off on a thin plate. You may also want to start off at a lower level. Again, if you see it's fine, you can always pump up the action. And now I've seen this, by the way, in a machine. One of my first trial cuts with somebody is he was actually holding it on a fourth axis turn head inside the milling machine. So your basic support, even though the plate was fine, but the basic support is between two centers. So the further out you got from the center, the more vibration you had. So you could not work at a high level. In that particular case, I even went down to 2. Okay. This I'm not going to talk about right now. I'm going to skip over this. Now, just to compare certain tests that we've done, this is a little pocket that we cut over here, was actually a piece of titanium. Now, doing it traditional way with, I know you guys are not ISCAR, but we did it on ISCAR. I'm sorry about that. But when they tried it with their most efficient way, they knew how to cut without iMachining. It took them 14 minutes to cut out this pocket. We use it in iMachining, change everything over to iMachining technology. It took them 3.5 minutes instead. Okay. We have also different types, different trials that we've done where we cut down, see, from 17 minutes to 6 minutes on aluminum. People say, how come? Well, aluminum, I can really work hard. So even aluminum, we're very efficient, a lot more efficient. Okay. Titanium is a phenomenal way to use, is an excellent case of where to use iMachining. Okay. And we also have what we call now also iMachining 3D, where it uses the technology that we know in iMachining 2D, but it optimizes the machine. What it does is it does the most deep cut as it can, but then as it has to, since it's shaped over here, it does what they call a step up on each area, and then make steps on the part itself. You can actually see the machining over here, and I'll show you a little film about this in the morning. Okay, it optimizes the Z slot cutting. It slices into Z's. Okay, going deep into the pocket, doing as deep as it can. As you see over here, it's going to do first the very bottom. You can see the trochoidal cuts in the corner. Then after that, it does a scallop going up. Okay, a controlled scallop, and accordingly, that's how it works. So certain areas, you tell it how big you want the scallop, and certain areas will have larger steps, and the steeper, it'll have smaller steps. You can see that immediately on this as well. And we can set the scallop, the size of the scallop that we want. Okay. Now, during the set of procedures, the actual depth of the cutter gets smaller. Now, let's take a look also in this particular part that I showed you before. Okay. It'll also only work where it needs to. Now, look at this. You see it's working only on that side now, doing its step up. These walls were flat walls on the side over here. It doesn't have to do any kind of machining over there. So just working in the areas where it needs to work. Now, when it comes to using then afterwards a smaller tool to clean out the corners, it'll only work in those particular areas. And you can see that also very well over here. And I think, and I believe Zoro, you answered me before about the corners. As you can see in the corners itself, even there it did a trochoidal cuts. Okay. And whenever you have a lead into the part and lead out, is always in a tangent lead out, lead in with tangent, lead out always with an arc. So there's never any sharp turn. Okay? Okay, now as you're going up, okay, the cutting conditions are adjusted also automatically. Because over here you're cutting with, when you're down at the bottom, you're cutting with the full step of the tool. But as you go up, you're cutting with, there's less of the tool that's actually cutting. And as I said, the iMachining automatically determines the cutting conditions. Okay, now let's take a quick look at this film at how it cuts a 3D mold. Now you can see it's doing the, now this has to be done with a specific step down, because probably has to go further down over here. So note that it's cutting first, and now it's also starting to step up. Starting to step in. The tricordal cuts in, and now it's stepping up. And also you can notice how it localizes itself to work only in a specific area and then moves on to a different area also. So you don't have this repositioning around the entire part. It always cuts out in those particular areas. Okay. Now, also iMachining is not only for iMachining 3D can also be used for prismatic parts. Okay. For instance, if I can do this part in iMachining 2D, no problem. No problem doing it. But with iMachining 2D, I have to program each one of these areas, each one of these depths have to be done in a different pocket. I have to do one operation after another operation after another operation. If I use iMachining 3D, it automatically recognizes the depth of each area and knows to work on each pocket exactly the way it should. Now, I should mention before, iMachining 3D is a roughing tool. Okay, it's meant for roughing. Now, prismatic part programming with iMachining 2D, as I mentioned before, you can see all of the operations needed just for this. If I use iMachining 3D, you can see that everything over here, we basically have two iMachining operations, one for the roughing and one for the rest materials, and then we just use different technologies for finishing. Okay. Okay, are there any questions at this point? Okay, by the way, I will make the PowerPoint available to all of you also later on, together with the recording, so you can see it. But I just want to go a little further on in here. Okay, and I mentioned before about, in the very beginning, I mentioned also it uses for indexial, or let me go further down in the presentation. I mentioned it also that it's used for mill turn. Inside mill turn, we also have it. It's very useful. So we'll take a look at this little film over here. Type of machine. All right, we start with the regular mill turn. That's fine. Now you can see this is a regular pocket over here, but I want to go a little further on in this presentation over here. Here we go. To this side, we get to the other side. You can see how iMachining is used over here inside a mill turn machine. In this particular case, the cutter can't go past half the way, so we do use the C-axis of the machine itself. You can see very clearly the tricordial cuts is doing on side over there. Okay. And we even have it on we're using iMachining 3D together with simultaneous 5-axis machining. Move it ahead a little over here. You see, we're using the maximum amount of the tool that we can. Basically does that around the part itself. Then when it finishes that, let's see what happens now. See, now it's actually working in a morph spiral around the part. And now over here, you can see the actual step up that it does on the material. So once we finish the roughing on this, then we just go into there's a lot less material left over now, a lot easier to do your 5-axis simultaneous machining. Okay. Okay. That's all I'm going to show you now, right now in this presentation. Are there any questions? I know we didn't touch on the program itself. I still have a few minutes left. And I can just start showing you certain aspects as far as setting up the part. Okay. So let me open the program. The bird does not come with the program. That's my personal photography. So. Okay, I'm going to load a part. In SolidWorks itself. We're going to do the setup. Now, before I actually start the actual setup itself, oops, sorry, my mistake. I was doing some, just before this, someone asked me to check something, so I forgot to put it back exactly where I was before. So just give me a moment. Let me just go over here. And there we go. Okay, that's why my SolidCAM didn't load. Okay. Usually I'm very well organized with this. So we'll just wait one more moment. Okay, something is not working correctly here. Very strange. Okay, I think I know why. Again, if anyone has any questions, you can always ask. Okay, I think I know why. Let me go into my add-ins. There we go. That's why. Okay. Okay, now SolidCAM is loading also. Usually I keep that on. Okay, just another moment. There we go. Okay, now I'm going to reload the parts that I want to work on. Okay, this is a pretty simple part, but it has several pockets. We have also a complete pocket over here. We have external pockets over here. And we'll create material as we go along the part. Now, when I go into SolidCAM, okay, let me just go for a moment into my settings, SolidCAM settings. And if I go down to my settings where it says iMachining, you'll note that I decided that most of the time, for some reason, I'm working on 1020 material. So I have in my default database that material. Doesn't mean I can't change it. And I'll show you this a little later on as we go. But just wanted to know if you see this material coming up automatically, you'll know why it's coming up automatically over here. Okay. So I'm going to start my program. I'll go to New, Milling. Okay, I'll create my coordinate system. I'm going to have it at the center of revolution face. I'll click on this face over here. So it's on the center of that revolution face. And I've already automatically created my stock. You can see my stock at this point is 2 millimeters around the part itself. I'm not going to do a face mill operation, so I'm just going to leave this here as 0, as if I did one already. Okay? That's my stock itself. We have our target, which I talked about before. Now let's go down here to the iMachining data. You'll note that my material that I'm going to be working on is a 1020, as I showed you before. However, if I click on this, you can see we can choose from all different types of material. And if somebody's asking me, thinking, okay, what is this material that doesn't exist over here? I can always go to edit my iMachining database. And let's see, right click and add a new material. And then when I add new material, what's important over here, where's my material? It's actually down here. Sorry. New material. There we go. You give the name of the material, whatever it is. Let's say 40.
Mnemonic.
What?
Mnemonic, for example.
I didn't hear exactly what you said.
Mnemonic.
Very unclear, but let's leave it at 44. I can't. It's irrelevant, really, what the name is. The name is I can give whatever I want, but something that makes sense. There's something here that's very important, and what you do is you just go into the internet, look up that particular material that you're using, and put in here the ultimate tensile strength. Okay, when you put in here the ultimate tensile strength, okay, let's say it's 1,000. Okay, I'm throwing out an example. I'll say apply, and I can do save and exit, and I'll have that material inside over here. So if I go now to choose it, I can go here, and I'll have that material over there. Okay? Again, you can give it any name you want. Obviously, you're going to give it a name that makes sense to you, or the actual name of the steel, and just look it up online, put the tensile strength, and that's all you really have to do. Okay. Now, as we get into it, there's a lot more. There's more you can play around, but for the basic use, that's all you really need to do. Okay. Also, the machine database. I have here something called Global Machine, which it actually looks at the information about the machine from the VMID that I put in over here. Sorry. That I put in. I clicked on that, except for that. Okay. My mistake over here. It looks for whatever it takes the the information from whatever's in my VMID, or I can create my own also as well. I don't have to use global. I prefer using global in most cases. This way, it automatically adjusts itself to the VMID of that particular machine. Okay, I'll click on exit. That's basically the whole setup. The setup is really very, very easy. Okay. Now, I know today we didn't do too much programming. It was important to me that you all see, get a little more of a background of why iMachining, what to do with how people, why iMachining compared to conventional machining, the benefits of the iMachining, how it can make your tools last a lot longer. Next week, and we'll actually go through programming with iMachining, and we'll go as far as deep as we can. It'll be probably next week and the week after as well. So we'll probably have 2 more lessons on iMachining itself. And of course, I've recorded this. And as I said before, the PowerPoint will be available to everybody, and I'll put the attachment inside the email itself, inside the invitation to the next webinar, to the next class that we have. Okay, are there any questions just before I finish off?
No.
Okay.
No.
Okay, excellent. All right, so again, thank you for joining me this time, and we'll see each other again next week, and we'll be again next Tuesday. Sorry.
Thank you.
Thank you very much.
Wednesday.
Thank you,
I'll
Sidney.
decide exactly as we go along. Okay, take care, everyone.
Thank you, Sidney. Take care.
Bye-bye.
Thank you.
Bye.